which is organized by the E&ICT Academy, MNIT Jaipur. So today that we will discuss the next topic. Let me share my screen. So in the last session that we had discussed the encoder decoder. And okay, so let me ask, is my screen visible to all of you? Hello? Okay, fine. Okay, fine. So last class, okay, fine, thank you. Thank you. So this encoder decoder that we had discussed in the last class, and I should say this is the first step to understand the uh, concept of transformer. So first you have to just know each and everything about this encoder decoder, and that was covered the complete one in the last session. So inside this encoder and decoder, actually the LSTM was there. Okay, and in this today here we will discuss the next step, that is the attention mechanism. So I will share one paper to you. Okay, and just you go through the paper, research paper. Now the point is, what is the need of this attention mechanism? So what was the problem in the encoder decoder? Okay, so first let's start the point, the disadvantage or the problem that encountered in this encoder decoder model. So problem in this encoder decoder is actually this was our encoder, okay, and here this one is a decoder, this one is the input sequence, okay, and this one is the context vector, and here that is output is there, and inside this encoder and decoder, okay, so LSTM that was explained, this LSTM, and here that is LSTM, and this LSTM and LSTM that is entirely different to each other. So now the point is encoder encode the given input sequence, okay, or this encoder that summarize the this input sequence, okay, and it will give you a compact representation, okay, and this compact representation we will send to the decoder, and the decoder, after looking this context vector or this summary of this input sequence, okay, it will print your output sentence, that is on a step-by-step manner, step-by-step basis. Okay, so the issue is the moment you give as an input sequence is a big sentence. This input sequence, that is a, let's say that is a big sentence. Okay, or that is a paragraph. Let's say. So the encoder was having to read a big sentence. So there was a problem in converting this entire big sentence or this entire paragraph into a context vector. Okay, because after all it is just a set of number. So in this set of number, okay, you will be able to store the summary, okay, the compact representation that you can call as a context vector. So this context vector, that is a set of number, that is a vector. And since this context vector was not being formed correctly, then the decoder was also not able to generate the word correctly. Okay. So this context vector that will get overloaded because the heavy load that will be on this context vector, because the input sequence is a big sentence or it's a paragraph. So this vector just is the heavy loaded just because of the big sentence, because the decoder that was also not able to generate the word correctly. So the mechanism was developed, okay, which we called as the attention mechanism. Clear? So let me just draw one kind of architecture of this encoder decoder, and then we will just go to the next this mechanism, that is attention mechanism. Okay. So now you see here that you can call as an encoder. So this LSTM, okay, and this is your H0, H1, H2, H3, and this H4, and same this one is also, that is H1, that is H2, H3, and H4. Clear? And the input here, that is turn. Here, this is the English input sentence. This one is a O, this one is a the, and this one is a like. Okay, so this one is the input sequence. So here, this point, the encoder generates the summary of sentence. Here at this, the encoder will generate the summary of input sequence, okay, that we call as a context vector. That is the context vector. So basically, we are generating the set of numbers that give you a summary of this given this input sequence. Okay, and this context vector, okay, we will just feed here in the decoder. This one is a decoder. So here, this one is a LSTM at t is equal to 1 time step, at t is equal to 2, and t is equal to 3, and t is equal to 4 times step. So now here, that is input, current input is, that is start, or in the paper that is EOS. EOS, that is the, sorry, that is not EOS, that is start of sequence. Okay, that is start of sequence, or we can say that is a start. Clear? And here the output, that is light. Clear? Here the output, that is a band, Hindi, and the output that is a karo, and here the output, that is end. Okay, and here the one more, that is hidden state, of decoder, this one is a S0, and this is actually the context vector, okay, that is coming from this encoder side. Clear? So now here this is S1, and this one is the previous hidden state of the decoder, S2, and this one is S3, and this is S4. Okay, so now the input is here, the current input is, that is light, okay, which is same as the output at t is equal to 1 of this LSTM. Here the current input is 1, which is the same, okay, the output at t is equal to 2 time step of this LSTM, second LSTM, third one, and the fourth one, that is correct. So this one is a Y1, okay, Y1, Y2, and Y3. Clear? So when you provide the teacher forcing, this one is a teacher forcing. Okay, that already I explained. Teacher forcing. Okay, teacher forcing means you provide the correct level here. Whatever be the output here, okay, whatever be the output here at the time of the training, you should provide here, that is correct input. Okay, that is a teacher force. Okay, so now this context vector, now this context vector that we will feed here to the this decoder, and now decoder step by step that print the output sequence. So this one is the output sequence, light one karo, and this one is the end, step by step. Okay, the first one at is equal to 1, that light was printed in step 2, the band was printed at t is equal to 3 times step, the karo that was printed, and this is how encoder decoder works. Clear? So this is the encoder decoder. So as I said, the problem is just this input sentence, this input sequence that we are feeding, or we are just giving to the this encoder. Okay. So the problem is, as soon as you start giving a little bigger sentence, or that is a big sentence, or it's a paragraph, then this context vector that will get overloaded. Okay, and just because of this, the decoder that will not generate the correct output. Now the point is, the problem is at the part of decoder side, not at the encoder side, because encoder, that is okay, this one, this is the context vector. Now the problem is at the part of the decoder, at the end of this decoder side part. Okay, so to print light, now the just you understand this point, now to print this light, did we need the entire input sequence turn off the light? Okay, the problem of decoder side is what? So to print light, do we need all this entire input sequence, or do we need a specific word? So the answer is, only I need this light, this word from the input. And if you knew the light from the input, you could print this light easily. If you know this word, then you can print easily this light. Correct? So the same, to print this band, do we need the whole input sequence? No. You only need these two input sequence, turn and off. Okay, so I guess you are getting my point. At any time step of the decoder, this one is at t is equal to 1, at t is equal to 2, at t is equal to 3. So at any time step of the decoder, we do not need the entire input sequence. Okay, we human beings are also just learning or just reading the in the same way as if we are given a very big or large sentence. Okay, and if let's say we are somewhere in the middle of the big sentence or a paragraph, then we catch or then we pick the main keywords. Okay, and we do the translation. So this is the concept using which human beings that perform the translation from one language to another language. So we pick some keyword, and based on the keyword, we we make one summary. We make one summary. Okay. So I mean to say that suppose you are at this time step one, this t is equal to 1 of this decoder, and you have to print this light. Then in some way you will have to pass this light information to the decoder. Okay, means at t is equal to this, at this one, this light at t is equal to 4. So you have to pass this light, means in English, from the encoder. Okay, you have to pass specific this light, this at t is equal to 4, from this encoder to the decoder to print this Hindi sentence. To print this Hindi sentence of Band, you must pass these two words, turn and off, and that is at t is equal to 1, and this one is at t is equal to 2. So we have to dynamically generate this information at every time step of the decoder. That the point is which time step or set of time step of the this encoder is important for you currently, and this mechanism that is called as the attention mechanism. I hope this point is clear to all of you. Okay, so now we come to know in this attention mechanism that we have to pass this light turn off, means this encoder, this encoder. Okay, we have to pass this information at every time step of the decoder. That which time step of the encoder is useful. Let me repeat, just to print this word, this light, just to print this light, we have to pass at t is equal to 4, the information at t is equal to 4 of the encoder. We have to pass this information to the decoder. To print this band, we have to pass these two information, this turn and off at t is equal to 1 and t is equal to 2 of the encoder to this decoder at t is equal to 2. So now point is, are you getting this point? So this this band or this curve, okay, this depends on the two input. This light, that depends on the two input. First one, that is the current input, and second, that is the previous hidden state. Again, just to print band, it depends on the this S1, that is a previous hidden state. Okay, so up to so far what has been done. Okay, so it depends on this S1. and this y1, that is the current input. Okay, so this was the encoder decoder model. Now in attention mechanism, we have to pass one more additional input here, this one more input. Clear? So that you can call as a C1, C2, C3 and C4. Means that is a context vector. So basically for any time step, we have to give the input of Ci, and the Ci we are calling the attention input. This Ci, that is called as the attention input. Okay, and this attention input basically it decide, okay, means this Ci, the C1, C2, C3, that it depends, that it will depend on, means that current, this output, that depends on the which one of the time step of the this encoder information. Okay, so for every time step, the input, for every time step, the input that should be the function of y I minus m1, s I minus m1, and c of I. Clear? So now question is, how does this ci look? So there are only two options. Okay, either it will be a vector, or it will be a scalar, or maybe it will be a matrix. And the point is, what should be the dimension of this ci? What should be the dimension of the ci? So then by looking at as a human being, I am understanding that this H4, that is the hidden state of the encoder, be the most useful, this one. So if someone magically tells me that which hidden state of the this encoder H1, H2, H3, H4, the which hidden state of the encoder is useful, so the job of the CI is just to put this H4 in C1, H4 in C1. So for time step 2, okay, for time this C1, C1 that is should be this function of H4. C2 that should be the function of this H1 and H2, because turn and off. Just to print band, the input that encoder should pass this information, this turn and this off, H1 and H2 to this C2. Okay, so one point is clear that Ci, it should be a vector, because you are picking up the this hidden state of the encoder. It is not a scalar. It should be a vector, because it depends on the this. It may be depend on one vector of this H, or maybe depends on the two vector that may be the function of H1 and H2. Ci may be the function of H1, H2, H3. It may be the function of H1, H2, H4. Okay, just to print the output of the decoder, this Ci that may be the function of only H1, that may be the function of H1 and H2. It may be the function of H2, H4, like, okay, it depends. So the dimension that should be the same dimension of this Ci that may be 1 Hi, okay, or maybe the function of 2 Hi. So this attention mechanism, okay, this attention mechanism then assign the weight, to all the hidden state of the encoder. So let's say this one is the start, okay, and this one is the H1, this one is the H2, this one is the H3, and this one is the H2. Okay, and here that is the alpha 1, alpha 2, alpha 3, and alpha 4. So that is C1, that should be equal to alpha 1 H1 plus alpha 2 H2 plus alpha 3 H3 and plus alpha 4 H4. And this alpha, these are the scalar. These are the weight. Okay, and C2, that is alpha 1, okay, H1 plus alpha 2 H2 plus alpha 3 H3 and plus alpha 4 H4, where H1, H2, H3 and H4 that are same, but these alpha, alpha I or alpha 1, alpha 2, alpha 3, alpha 4, okay, these are different than this alpha i's of C1. So alpha i's of C2 that are different than the alpha i's of C1. Correct? And here that is I will just denote this notation I, that is a time step of the decoder. Time step of decoder. And J, that is a time step of encoder. Okay, so now this Ci, that is sum of alpha ij hj. Okay, so now C1 is equal to alpha 11 h1 plus में alpha 12 h2 plus alpha 13 h3 plus alpha 14 h4. Okay, and C2 that you can write this alpha 21 h1 plus alpha 22 h2 plus alpha 23 h3 plus alpha 24 h4. And total number of alphas, that is equal to I cross J. Okay, so now let's discuss how these alpha that are calculated. So alpha that are the scalar. Alpha that is a scalar. Okay, these are the scalar. And this H, these are the vector. And this one is a scalar. Okay, now Ci, that is the extra input. Here, this one is the Ci, C1, C2, C3, C4. Okay, so now the point is, first let us understand the meaning of this alpha 11, alpha 12, alpha 21, alpha 22, alpha 23, and so on. So let's say alpha 21, this one, alpha 21. So this alpha 21, that is the alignment score or similarity score. This one is alignment score or similarity score, which tell me that two time step of decoder, how much role will the first time step of encoder, that is H1. Clear? Yes or no? This alpha to 1, okay, this will give us the information at t is equal to 2 time step of the decoder, okay. So just to print this band, if you just compare with this, just to print this band, okay, what is the role or how much of the role of this H1? Alpha 22, alpha 22, just to print the output of the decoder at t is equal to 2 time step, how much the role of this at t is equal to 2 time step of the encoder. Alpha 23, just to print this t is equal to 2 time step of the decoder, that is a band, how much role of this at t is equal to 3 time step of the encoder. So I hope this point is clear to all of you. So that is alpha 11, alpha 12, all alphas. Yes? Is it clear to all of you? Alpha 11, alpha 12, alpha 13. So alpha 21, this alpha 21 that depends on alpha 21 that depends on H1 and S1. H1, that is S1 is previous hidden state of the decoder. Okay, and H1, that is at t is equal to 1 time step of the this encoder. So what you want to find out through this attention mechanism, you want to find out that whatever translation that has been done till now, this S1, whatever the translation that has been done till now, okay, means up to this t is equal to 1 time step, okay, on the basis of the translation of this S1, on the basis of this S1, S1 is the translation that has been done till now, okay. So now to print the output in time step 2, how useful the first time step of the encoder. This is the alpha 21. So just you listen again one more time with this alpha 21. Okay, we don't need the information that how much the output of the second time step of the decoder depends on the first time step of the encoder. So now this alpha to 1, okay, so just to print this light, okay, so the how much the role that will play to print this light, okay, of this H1, how much of the role that will play to print this light, the H2, and how much the role of this H3 to print this light, how much the role that will play this H4 to print this light, okay. So we don't need this information. What we want, based on the translation that has been done so far, that is the S0, okay, now to print band based on the translation that has been done so far, that is S1, to print this curve, that is t is equal to 3 times step, based on the translation that has been done so far, that is S3. Now what and how this H1 are useful to print this output, that is a karo. That is a alpha 1 2, alpha 1 3, alpha 1 4, and alpha 2 1, alpha 2 2, alpha 3. Clear? So now alpha 2 1, that is a function of H1 and S1, and alpha 2 3, that is a function of this H3 and S1. So alpha ij, that is a function of Hj comma Si minus 1. Clear? I hope this point is clear to you. And this one is a translation that has been done so far, and this one is the hidden state of the encoder. So accordingly, just you decide this alpha 1 1, what exactly it gives you the information. Alpha 1 2, alpha 1 3, and alpha 1 4. And likewise, this alpha 2 1 and so on, this alpha 3 1 and so on, and alpha 4 1 and so on. Clear? So now the question is, what is this mathematical function? What is this mathematical function? So here the researcher that has used a neural network approach. This one is a neural network approach. So now I tell you, sorry, yes. So neural network. Okay. So this one is the kind of, you can say, that is a ANN, that is artificial neural network, and this one is a S1. Okay, and this one is a H1, and this one is a alpha 2 1. Okay, and this alpha 2 1, that is a function of H1 and S1. So this function is the artificial neural network, okay, neural network, which has its own weight and this bias. Okay, so now the question is how this network be trained, how this network that is trained. So now this one is a very simple. Okay, so this weight and this bias of this, okay, so when whole this architecture is trained, along the way it will also train itself. Clear? So now up to so far is okay. Is there any doubt? Okay. So now let us understand how to generate this alpha. Okay, this alignment score, the similarity score. So this CI, that is sum of alpha ij and hj. Clear? So now this one is a kind of neural network. In that neural network, okay, this one in this neural network, that we will give the input of two things. First one, that is a S I minus 1 and Hj. And this neural network that will calculate the weight, and that it will give me the Eij. Okay, so now here this one is a neural network. Okay, so I will give you the I will give this neural network to this one as I minus m1 and this h of j, and it will give me the Eij. Okay, and apply the softmax on this Eij. Here, just you apply the softmax on this Eij. And from this, I will get my alpha ij, alpha ij. So now let me explain in detail. Okay, so now the architecture of the decoder is, this one is the architecture of the decoder. Here, this one is the LSTM. Okay, this one is the start, this one is the light, this one is the fun, and this one is the from. So here the input is this, sorry, output of the LSTM at different time steps, and this. So here now that is a S node. Here this S1, this one is a S2, this one is the previous hidden state of in this decoder. Okay. So the point is the architecture of the encoder that remains same, but in decoder you actually make a change in it. You add a neural network here. Okay, that is a feed forward neural network. So in this only that is one hidden layer, and there are three number of, let's say three number of neurons are there, and one output layer. This one output layer and this one hidden layer. Obviously, that is input is also there. This one is the input layer. This one is the hidden layer. This one is the output layer. Okay, that is a neural network. Simple feed forward neural network. So all these are there's no H1, okay. These are the vector. Let's say this H1, that is a vector that is A, B, C, D. That is a four-dimensional vector. Okay. And S node, this S1, S2, S3, that is a four-dimensional vector. So S node, let's say this one is a four-dimensional vector E, F, G, H. And now you see the flow of this architecture. So first, you give the input, the sentence to the decoder. Okay, clear? This one, this start, this light, this bun, and this one. Okay, clear? So now C1 is what? This one is C1. Okay, C1 is sigma of this alpha ij h of j. So that is the function of this alpha 11 h1 plus में alpha 12 h2 plus में alpha 13 h3 plus alpha 14 h4, and this one is a CS1. So first of all, you have to bring this S naught, okay, this S naught, and put this S naught here, the input vector. Here the input vector. Clear? And you have to concatenate this S naught with H1, H2, H3, H4, and H4. Sorry, H1, H2, H3, and H4. Basically, you have to form a one matrix in which 4 rows and there are 8 columns. So, what would be the matrix? So now S naught 1, S naught 2, S naught 3, S naught 4. Okay, H11, H12, H13, H14. So let me explain this matrix: S naught 1, S naught 2, S naught 3, S naught 4, and H21, H22, H23, H24. And here that is S naught 1, S naught 2, S naught 3, and S naught 4. This H31, H32, H33, and S34. And one more, that is S naught 2, S naught 3, S naught 4, and H41, H42, H43, and H4. Clear? So now this is the first number of S naught. This is the second number of S naught. This one is the third number of S naught. This one is the fourth number of S naught. And this one is the first number of H1, second number of H1. Okay. Then third number of H1 and fourth number of H1. Now pick up this each row. This S naught actually this one is a vector. H naught that is a vector. H1 again that is a vector. Okay. So now pick up each row of this matrix one by one and put it into the this layer here, this side. 1, 2, 3, 4, 5, 6, 7, 8. So this feed forward neural net. Second time, the second input of the matrix. Third time, that is the third row. Fourth time, that is the fourth row of this matrix. This. So basically, you have to put this S I minus 1 and this Hj in concatenation. In concatenation. And since you have this fully connected, layer, okay, so your weight that will be this side, that is 8 cross 3. That is the input layer to this hidden layer. And here the weight, that is 3 cross 1. Okay, so either you send one by one, means the one by one row of this matrix, or you can send this whole matrix at once, okay, as a batch operation. So you can send a batch of this 32 or a batch of 64. So here, suppose we are sending a batch of 4. So this matrix is 4 cross 8. This matrix is 4 cross 8. And what will happen in forward propagation? So this matrix will be the dot product with the weight. Okay, here the weight, that is 8 cross 3. So now that is 4 cross 8 and 8 cross 3, that is 8 cross 3, that is the weight. Okay, so now this will be your 4 cross 3. Now we apply this any non-linearity on this one, 4 cross 3, maybe the 10H. Okay, so I will add the bias also. So whatever it is, even after doing all this thing, this activation function and adding the bias and all these things, I still have 4 cross 3. That I still have the 4 cross 3 matrix. Now I will do the dot product of this 4 cross 3 with this weight, that is 3 cross 1. Okay, so now this 4 cross 3 with this 3 cross 1, so the output that is 4 cross 1. And 4 cross 1, that is a E11, E12, E13, and E14. Now see this one. Yeah, this one. That is a E11, E12, E13, and E14. Okay, so these are the alignment scores. Okay, but these are not in the form of the normalized vector. So I will apply the softmax. Okay, this one. So the alpha ij, that is after the softmax, E of this, let's say alpha uh, 1 1, that is E of exponential of this E11. Okay, exponential of E1, sorry, exponential of this E11 plus exponential of E12 plus exponent, I should write here, you should not confuse with the E and E. So this alpha 11, that is exponential of E11 divided by exponential of E11 plus में exponential of E12 plus exponential of E13 and plus exponential of E14. Okay, so and alpha 12, that is exponential of E12 and the remains same. And likewise, that is alpha 13 and alpha 1. Okay, and if I add this all alpha 11, alpha 12, alpha 13, alpha 14, then I will get equal to this 1. Okay, so now C1. So now I got this C1 because H11 that we know, and alpha 11 H1 plus में alpha 12 H2 plus alpha 13 that is H3 and plus alpha 14 that is H4. So H1 H2 H3 H4 that we know already. So alpha 11 alpha 12 alpha 13 and alpha 14 that we got from this side. Okay, so this yt minus 1 and this C1. So now LSTM that will give the y of t, and y of t is, that is a light. Okay, so this is all about this I is equal to 1. So now at I is equal to 2, so we have to calculate the C2, and C2 that will be alpha 21 H1 plus alpha 22 H2 plus alpha 23 H3 plus alpha 24 H4. And here the matrix that will be S11, okay, S12, S13, and S14. Okay, H11, H12, H13, and H14. So here that is S11, S12, S13, and S14, H21, H22, H23, and H24. So S11, S12, S13, and S14. So S3, sorry, H31, H32, H33, and H34. Here the S11, S12, S13, and S14, and sorry, H41, H42, H43, and H44. Okay, so now you see this one is same. Okay, if you compare this to this, then this to this right side, that is same. Okay, so now again that is, this one is a 4 cross 8 will get multiplied by this 8 cross 3, that is a weight. So that is a 4 cross 3, and 3 cross 1, that is a weight. Again, now if you multiply this 4 cross 1 and so on. And this 8 cross 3, just remember this 8 cross 3, these weights are same. So these weights that will not change. these weights that will not change. Okay, so these weights that will change when back propagation that will be applied. Okay, and when will the back propagation be applied? When your decoder that will print the last word. So now you compare this y cap, okay, whatever it will be y cap with the y, okay, the true output. That is through the categorical cross entropy, that is the loss function. And the error will back propagate and will flow through this entire network and will update this weight terms. Now, as soon as the next sentence that will come, H1, H2, H3, H4 will generate, and then on these weight, this weight, okay, that is updated weight. Okay, on the basis of this updated weight that we will calculate this C1, C2, C3, C4. Okay, and so on. So important is this whole neural network, okay, since it is same for every time step, okay, this one. This one. So this whole neural network that is same for every time step of the decoder. So this is called as the distributed fully is the distributed fully connected neural network because these weights are same for all the time steps of the decoder. Clear? Is there any doubt? Is there any confusion? So let me summarize this whole lecture. So actually we studied the encoder decoder, okay, and the main problem of in this encoder decoder is this one is the encoder and this decoder is connected through this context vector, and this context vector is a summary of this input sequence, okay, and this is in the form of the vector. If suppose we have the very big input sentence or we have a, let's say, big paragraph, okay, then this context vector, okay, node that will come on this context vector, and just because of this context vector maybe it cannot recall all the information, so the output of the decoder that will not correct. Okay, that is the problem in this encoder decoder model. So now the mechanism that has been set up that we call as the attention mechanism. So here the architecture of this encoder decoder is this one, and just to print the output of this LSTM here in the decoder, this S0 and this S0 is the S0 is the previous hidden state. S1, S2, S3, S4 that is the previous state of the encoder, and S4, S3, S2 that is the previous hidden state of the encoder. So now to print any time step of the decoder, okay, from this LSTM, and different time steps. We need only the two input. First one is the current input. Okay, clear? So current input, that is light start, light band, and this one thorough. That is the current input, and the second input is this one, S0, S1, S2, S3. Based on these two input, the output, okay, the decoder that will print step by step at t is equal to 1 time step light, t is equal to 2 time step band, t is equal to 3 time step thorough, and t is equal to 4 time step, that is the end. Clear? So, but the point is, do we need to print this light, that is at t is equal to 1 time step, the decoder, the output of the decoder at t is equal to 1 time step? So do we need all this sentence at a time? No, only we need one specific input. Okay, so that is actually, that is a weighted sum. So we need a one weighted sum. Okay, so means that is the extra input along with this S0 and this current input. S1 and this current input along with this S2 and current input along with this S3 and this current, this input, that is this one. Okay, we need one more input. Okay, so this input, this C1, C2, C3 and C4, okay, this will be the weighted sum of this H1, H2, H3 and H4. This will be the weighted sum of this H1, H2, H3 and H4. And based on this, okay, so how much of the role of this H1 to print this light, how much of the role of this H2 to print this bun, okay, how much of the role to print this curve of this H1, H2, H3 and H4. So let me repeat, just to print this light, H3 and H4. Clear? So that is a weighted sum. So that is a one mechanism that we call as an attention mechanism. So attention, we have to give a focus to at which this hidden state of the encoder. Clear? So now we have to, for this CI, we need to find this alphas. Alpha 11, alpha 12, alpha 13, and alpha 11, alpha 12, and so on. This one is the alignment score, similarity score. So now I explain the meaning of this alpha ij. Okay, that is a similarity score. So this alpha to 1 that I explained here, this alpha to 1 that depends on the H1 and S1. Okay, so which tell us to print at t is equal to 2 time step of the decoder. So how much of the role that will be the first time step of the encoder? Alpha 2 just to print at t is equal to 2 time step of the decoder, how much role that will the first, sorry, the second time step of the encoder, means that is H2. Clear? At t is equal to 2 time step of the decoder, how much of the role that will be the third time step of the encoder, that is H3, and so on. So these are the alpha ij. So now after the calculation of this alpha ij, now I will put here this in C1, C2, C3 and C4, because H1, H2, H3 and H4 that are fixed. Okay, but these alpha ij that are different. Okay, so alpha ij for this C1 and alpha ij for this C2, and both are different. Both are different. Clear? And this is kind of the representation of alpha ij, that is a function of hj and si minus m1. So si minus m1, that is a previous, this hidden state of the decoder, and hj, that is the hidden state of the encoder. So now I replace this function with this kind of the feed forward neural network. Okay, and the input is, that is a concatenation of this si minus m1 and hj. So here this one, and the one hidden layer, that is, let's say for example the number of nodes that is 3 and single output. Okay, and this one here the input is Si minus M1 and Hj. So Si minus M1 and Hj, that is this one, that is in the form of the one this matrix. So you can send this row in a one time, the second row in a different time step. Okay, clear? So now this one is a kind of small calculation, and this 4 cross 1, the 4 cross 1, this one is the Eij. Okay, clear? And this Eij, that is not normalized, so we have to pass this Eij through a softmax function. Okay, and sum of all this one, that will be equal to 1, and that is my alpha is this one here. And from this alpha ij, now I can easily calculate this ci, and ci, that is the extra, or that is the third input of at every time step of the decoder. Clear? So now this is kind of all about the attention mechanism. So now attention mechanism. So now if you have any, then please let me know. Attention mechanism. So in this session of this attention mechanism here, and let's take a break of 5 minutes. Okay, and the next session that we will start at 11:20. Okay, voice is breaking. Hello. So now, if you have any doubt regarding this attention mechanism, now you please write in a chat box. Again, in the next session, I will again brush up the complete thing. Okay, now in the first 5 minutes. So now the next session that will start at 11:30. Okay, I will again just repeat 11 minutes. So topic in continuous repeat in a first session. We'll discuss the next topic. We'll discuss the next topic. That is the transform. This topic, that is the transform. Attention mechanism. Attention mechanism. Important one. Okay, okay. So yes, I understand. Okay, okay. At my side. At my side. Okay, no issue. I will explain this whole thing in the first 5 minutes of the next lecture. Okay. At that time, just you see. Okay. And if you will be having any doubt, then please ask me at that time. So okay. So let's take a break. Okay. Yes. Thank you. Thank you very much.